Now, let us go to the very first network model that we will be talking about, and that is the minimum spanning tree. And let me give you a base example. So let me give you time to read the problem. Okay, now in this problem, there are seven cities, and I hope you are able to understand that these seven cities will eventually be our nodes. Okay, and according to the problem, we will be constructing roads so that one any person can move from one city to another. And and as we discussed the definition of edges, I hope you are able to understand that these roads will now be represented by edges. Okay? And just to give you an idea of how to or to give you an idea on how the graph of this problem looks like, we have this example. Okay, so we have the seven cities A, B, C, D, E, and T. We have the roads in between a pair of cities, or in this case, a pair of nodes. The numbers here represent the length of the road that will be constructed, for example. And our goal right now is to look for what we call a minimum spanning tree. Okay? Now, in order for us to look for the minimum spanning tree, what we need to do right now is to define what a tree is. Okay? Because after we understand what a tree is, then it is easy to understand what a minimum spanning tree eventually will be. Okay? So what is a tree? A tree is a connected graph with no cycles. So as you can see, we have three kinds of graphs. G1, graph 1, G2, graph 2, and G3, or graph 3. G1 and G3 are connected graphs. I hope you can clearly see that all nodes are connected to each other in G1 and G3. And I hope it is also clear that G2 is not connected. Okay? So based on the definition of a tree, the first definition, G2 is not a tree anymore. Okay? Next, between G1 and G3, G1 is not a tree. Even if G1 is connected, okay? Even if G1 is connected, the second definition requires us that a tree will have no cycles. Okay? However, as you can see in G1, we do have a cycle. No? And as you can see, this triangle represents the cycle between these three nodes. And therefore, G1 is not a tree because it contains a cycle. G2 is also not a tree because it is not connected. And in this case, G3 is a tree. So once you know the definition of a tree, what is now a minimum spanning tree? So let me read. The minimum spanning tree of a graph G is a subgraph of G with no cycles and which gives the minimum total distance or cost. Okay? So if you have a graph G, the minimum spanning tree of graph G is a subgraph of G. So what does that mean? Well, uh, in literal terms, you can find the minimum spanning tree within the graph. Okay? And how do you look for this minimum spanning tree? The minimum gives away the how. No? The minimum tells us we need to look for the tree. So remember, it should be connected and there shouldn't be any cycles. And in this case, the total distance or cost should also be minimum. The following gives you a way to determine or to define a tree of n nodes. No? So if you have a graph with n nodes, you will be able to check if a subgraph of G is a tree if first, no, the graph is connected, second, the graph has no cycles, and third, the number of edges in the graph is n minus 1. In fact, this paragraph, this point tells us that given these three uh, conditions, you only need to satisfy actually two of them. So what do I mean by this? For example, if your graph is connected and the graph has no cycles, then obviously the number of edges in the graph is also n minus 1. Okay? Next, if your graph is connected and the number of edges is n minus 1, then surely you won't have any cycles. Why? For example, let's say you just have three nodes. Okay? In order for you to connect these three nodes, you only actually need two edges. So for example, let's say this and this. So as you can see, if the graph is connected and the number of edges is n minus 1, so in this case 3 minus 1 is 2, then surely your graph will not have cycles. Okay? And finally, if your graph doesn't have a cycle, okay, and the number of edges is also n minus 1, then surely the graph is connected. Why? Because the only time the graph is not connected is if you have n minus 1 edges, but there exists some cycle. So for example, let's say you have a graph with 4 nodes. And let's say for this graph with 4 nodes, you need 3 edges for it to be connected, correct? So let's say the 3 edges is 1, 2, and 3. Now, even if in this graph we have 3 edges already, but because there exists a cycle, therefore, we cannot say that the graph is connected. So the only time that we have a tree given the two conditions is that, for example, let's say again, we have four nodes and we have exactly 3 edges and there are no cycles. Therefore, the graph is connected. So all you have to remember is, are these 3 conditions, and that you only need to um, confirm 2. If you can confirm at least 2 of them, then what you have is a spanning tree. And all you have to do is to look for a tree that will minimize the total cost and total distance to give you the minimum spanning tree. Now, there are actually a lot of solution methods that were developed by computer scientists, physicists, and mathematicians before. What I have here are the 4 algorithms that are very popular. Kruskal's algorithm, the reverse delete algorithm, or it's the reverse Kruskal's algorithm, these two. We also have the Prim's algorithm developed by Wojtek Jarnik, I think, no, in 1930, and it was rediscovered by Prim and Dijkstra in 1957 and 1959. And finally, we also have Boruvka's algorithm, no, discovered by Otakar Boruvka in 1926. Now, for our purposes, we will only discuss these two uh, methods. I think these two are very intuitive and easy to understand, and that is why we will just be limiting these our discussion to these two solution methods. Now, this slide gives you the pseudocode of the Kruskal's algorithm. There is a mathematical or computer science code, no, in order for us to apply the Kruskal's algorithm. But I think for us to easily understand how the algorithm works, it is best for us to see and understand the pseudocode or the code in English. And let me read the steps, no, the steps of this algorithm. First, you sort all the edges from the lowest weight to the highest. Then, after sorting all the edges, you take the edge with the lowest weight and add it to the spanning tree. However, you only add the edge if it does not create a cycle. Because if adding the edge creates a cycle or created the cycle, then reject this edge. As you remember, a tree will not contain a cycle. And therefore, if adding the edge created the cycle, then reject it. You keep adding edges until we reach all vertices. Or, if you remember two of the conditions, the three conditions given a while ago, we actually only need to add edges until the total number of edges is n minus 1. Okay? That's the Kruskal's algorithm. Now, for the reverse delete algorithm, we have this pseudocode. Again, we sort all the edges of the graph in a non-increasing or, in this case, decreasing order of edge weight. No? So you sort it in decreasing order. Next, you pick the highest weight edge from the remaining edges and check if deleting the edge disconnects the graph or not. If it disconnects the graph, then you don't delete it. Else, you delete it and you continue on. No? And finally, you keep on deleting the edge or removing the edge until we reach all vertices. Or again, if the number of edges left is n minus 1. And as you can see in this slide, we have the words addition and subtraction beside the Kruskal's algorithm and the reverse delete algorithm. Now, why did I have the word addition beside Kruskal's algorithm? If you remember, or if you look at the pseudocode, you're actually adding edges to your node. No? Starting with the edge that has the lowest weight, you will add, okay, to the spanning tree. On the other hand, in the reverse delete algorithm, no, you will be removing or deleting edges. Okay, you will be deleting the edge, and that is why I placed the word subtraction, because for the only thing you need to remember in the Kruskal's algorithm is you will be adding edges, and in the reverse delete algorithm, you will be subtracting or deleting edges. Okay, so now let us apply the Kruskal's algorithm into the base example that we have. Okay, so what I have here are the 7 nodes. So O, A, B, C, D, E, and T. And what I have here on the right is a list of all the edges, no? Sorted from the lowest distance, the one with the lowest distance, up until the one with the highest or biggest or longest distance. Okay? And according to the Kruskal's algorithm, you start adding the edge, and as long as adding the edge will not create a cycle. Okay? And of course, because we are looking for the minimum spanning tree, we will start with the cheapest. So the cheapest here is BC. So we can add BC, the edge BC with the distance of 1. Okay? Next, DE. Will adding DE cause a cycle? No, So we can also add DE with a distance of 1. OA is a 2. AB is a 2. And adding AB will not cause a cycle. Therefore, we can add AB. BE is a 3. And adding BE will not cause a cycle. Therefore, we add BE. Okay. OC is a 4. But adding OC, look, adding OC will cause a cycle. And therefore, we don't add OC. Even if it's cheap, no? Because at a distance of 4, it's the next cheapest right now. Okay, so we will not add OC. Next, BD. So OC is a cross. BD. Adding BD will also cause a cycle. So as you can see, adding BD will cause a cycle, and here's your cycle, and therefore we will not add BD. Okay? Next, CE. Where is CE? CE will also cause a cycle, and therefore we will not add CE. Next, OB. OB will also cause a cycle, and therefore we will not add OB. Next, DT. Adding DT will not cause a cycle, therefore we connect D to T with a distance of 5. And in fact, at this point, we can actually stop the algorithm. Why? Because given that we have 1, 2, 3, 4, 5, 6, 7 nodes, we actually only need 6 edges to be able to get a spanning tree. And in this case, we already have 6. 1, 2, 3, 4, 5, 6. So surely all of these other or remaining edges will not be added. No? Remember, this is addition. Okay? All of these remaining edges will not be added to the graph. And what we have here is the minimum spanning tree of the graph in our example. And what is the total distance? The total distance is just the sum of all the distances. So this is 5, 8, 9, 14. Okay? So this is how the Kruskal's algorithm is applied to our example. Now, to apply the reverse delete algorithm, no, in the same example, and what we have here is the graph G of our example. Again, I also have the list of edges, but it is now sorted in descending order, because remember, for this algorithm, this is actually an algorithm that we will delete edges, no? Or subtracting. We are subtracting edges. And therefore, let me get my eraser tool. And according to the algorithm, we will start with the edge with the highest distance first. So we remove 80. And because removing 80 will not cause a disconnection, then we can remove 80. Okay? So we remove 80. Next, how about AD? Will it cause a disconnection? AD is here with a distance of 7. It will not cause a disconnection. So we will remove it again. How about ET? Removing this will also not cause a disconnection. Therefore, we can remove. Okay? How about OB? OB will not cause a disconnection. Therefore, we can also remove. Okay? How about DT? For DT, if you remove dt, then you will cause a disconnection for t. And because it will cause a disconnection, we will leave dt. Okay, that's one. Next, how about OC? OC, we can actually remove. BD, we can also remove. Okay? CE, we can also remove. And at this point in time, we can actually stop. Why? Because the remaining number of edges is already 1, 2, 3, 4, and 5. And because there are 7 nodes, therefore we need 6 edges. And therefore, surely, we have the first here, dt. Surely, these 5 remaining edges will not be deleted. Why? Because the deletion of these edges will cause a disconnection. Look, if you remove BE, if you remove BE, then you will cause a disconnection between this graph and this graph. Okay? And therefore, you cannot remove BE. And the same thing applies for the rest of the edges. And what we have here is the minimum spanning tree using the reverse delete algorithm with the total distance again of 14.